Hi guys, BuildZoid here, and I finally got around to measuring the core voltage regulation of the ASUS Crosshair X870E Hero and the ASUS Strix X870 ITX boards. Both boards were provided by ASUS, so big thank you to them for sending them over for testing. And with that out of the way, let's get into it. And the first thing I should point out about this data is that if you're running your CPU stock or you're just doing like PBO overclocking, this data is almost entirely useless to you because AMD's boost system is designed around very shallow load lines. Very shallow load lines inherently have a lot of undershoot, they have a lot of overshoot, so like technically they have bad voltage regulation. The CPU doesn't care because that's what clock stretching is for, right? So when you're running PBO or just running the CPU stock, if the voltage undershoots by a massive amount, the CPU will just temporarily slow down. It won't crash. If you're doing static overclocking, the voltage undershooting by a significant amount is actually a major stability concern. But yeah, on PBO or stock operation, it doesn't matter. And that's why the stock load line on basically every AM5 motherboard ever is really, really shallow, and the resulting voltage regulation is technically bad. The other thing is, if you're messing with PBO, this is something I've run into in the past. I haven't really checked it recently, but you might find that actually setting the load line even shallower than stock will give you better performance. So if you have an ASUS board, it might be worth trying level 8 LLC. It might give you a slight performance bump if you're running PBO or even if you're running the CPU stock. Because, yeah, it does make the voltage regulation even worse than the default settings, but the boost algorithm just doesn't care. And having the average voltage be slightly higher will potentially give you more boost. So even though the actual voltage regulation itself is getting worse. Also, if you're wondering like, oh, doesn't the clock stretching cause any kind of performance anomalies? Nope, because when I'm talking about undershoot here, we're talking about like events measured in the microsecond time scale. You won't notice. Like you actually, yeah, like you won't notice, and you won't even really be able to measure it in like benchmarks, which is why, like I said, sometimes going to level 8 LLC will actually give you a performance increase, even though the voltage regulation gets even worse. Anyway, the other thing is this behavior isn't unique to Ryzen CPUs. NVIDIA GPUs have functioned like this since the GTX 900 series, and Intel CPUs as of recently have also started having these mechanisms built into them. So yeah, now if you're doing static overclocking on Ryzen 7000 series, the clock stretching functionality gets completely disabled. I haven't checked if that's also true for 9000 series, but basically that means if you're trying to run static overclocks, suddenly having significant amounts of undershoot becomes a problem from a stability perspective. Whereas if you're on PBO, it's just whatever. It looks really ugly on the oscilloscope, and that's about it. The CPU doesn't actually care. Oh, and for overshoot is only really a concern if it gets so high that it's actually harmful to the silicon, which is not the case with any of the data that I have here. So anyway, yeah, that's kind of that, and let's get into the results, I guess. Well, first test methodology and then the results. So for taking these measurements, I'm using a modified Ryzen 9 7950X, and by modified I mean I've run a twisted wire pair over to here, and I'm on the wrong layer. Anyway, so over to here, and then this connects to a piece of coax that goes over to the oscilloscope, and there's a 50 ohm termination at the oscilloscope. Now I'm measuring from over here because this is as far away from the Vcore VRM as you can get. With how much current the CPU is pulling, you will actually get a higher voltage measurement if you measure on this side than if you measure on this side, which is just kind of fun. Also, it's not unique to CPUs. GPUs have the same thing. Like depending on which side of the GPU core you measure on, you'll get slightly different voltages. With the CPUs, it tends to be more extreme because there's more resistance in the connection to the motherboard. Also, motherboards just generally kind of don't have that low resistance power planes compared to GPUs. So Yeah, so that's why I'm measuring from over here. Obviously, in a perfect world, I could get a measurement directly from the DyeSense, but that's just not practical. Though this gets pretty close because it will generally not measure significantly higher or lower voltages than what the DyeSense measurement would be. Whereas if you're measuring from like the back of the CPU socket, you get significantly higher average voltage. If you measure on this side, I'd imagine you'd also get significantly higher average voltage. Um, so yeah, so that's how I'm taking the measurements. For the actual load scenarios, I'm running Prime 95 192K FFT size AVX2. AVX2 because the 7000 series, if you run AVX 512, actually pulls less power, not more. 9000 series, it's the other way around because 9000 series has full AVX 512 support. So if you use AVX 512, they pull even more power than they pull on AVX2, but 7000 series AVX 512 runs less, is less power hungry than AVX2. The target voltage for this is about 1.095 volts. That's the average voltage. That's the target average voltage, not minimum or like maximum. And the reason I'm going with that voltage is it's about as much as I can cool with the 240 millimeter AIO that I'm using for this setup. So not the absolute limits of what you could run in this load scenario. Obviously, if I just went with more cooling, we could probably get away with like maybe 1.15 volts, maybe. But yeah, like at 1.095 volts, this workload gets very, very hot. Anyway, Prime 95 192K FFT size fits within the L3 cache of the CPU, so it basically doesn't care about memory settings, though memory settings are, like I'm running the same memory settings for every motherboard that I'm testing here. And, well, that's mostly for the Y-Cruncher test, but which does care a lot about memory. But, yeah, so it fits in the L3 cache, and that means it doesn't really load cycle. It's basically a constant load, and then the transients are caused by things like the Windows event timer and handling mouse input. So here we have, what it looks like when Prime 95 192K FFT size is running. This is at 10 milliseconds per division, and we're getting these periodic spikes here. These are caused by the Windows event timer. Typically that runs at 64 hertz, though if you're playing a video or something, that'll actually ramp up to 1000 hertz. But since this is just running Prime 95, it's ticking along at 64 hertz, and so we get a spike every 16.25 milliseconds, if I remember correctly. And every time the Windows event timer does its thing, it interrupts the Prime 95 workload, which creates this kind of spike where here we have Prime 95 doing Prime 95 things, then it gets interrupted, which causes the voltage to shoot up. And then once the workload resumes, the voltage undershoots quite significantly over here. Now, the other thing I'm doing while Prime 95 is running is I'm actually jiggling the mouse around because handling mouse input also interrupts the workload. And in a lot of scenarios, it's a lot more of an interruption to the workload than the Windows event timer. I do believe this measurement is from level 7, not level 8. And you'll notice that, like, yeah, we don't have the undershoot for the event timer really visible anymore. But this right here, which is a mouse input event, yeah, that's not great. And if we zoom in on that, we basically see the same thing, right? Prime 95 doing its thing, then it gets interrupted, the mouse input gets processed or something. I guess at this point, Prime 95 might be partially running, like some of the threads might be ramped up again. And then it resumes and we get undershoot over here. Though not very much because we're running a, this is with a droopier LLC, this capture is. So, and this is at 100 microseconds per division. Right, so from like here to here is 100 microseconds. So this is very, very, like these events are very, very short. The like Windows event timer interruption, right? Like this is at 20 microseconds per division. So that's even shorter because that right there is 20 microseconds. So this is like, I don't know, 5. Nah, like this is, well, it's not 10. Actually, yeah, so it's probably like 5. That's like 5 microseconds for, actually, it might be even less than that because technically the workload probably resumes somewhere around the peak of that, considering how this ramp doesn't, like it doesn't level off, it just shoots down. So, yeah, that's the test scenario and the measuring for Prime 95. Now, for Y-Cruncher, I'm running 22 gig memory size and 20-second loops. So in Y Cruncher, you can set how long it runs each whatever it is that it does for however many seconds. By default, it runs, I believe, 1 or 2 minutes. But because of the way I'm taking these measurements, where I'm taking 1,000 samples at 10 milliseconds per division, um, the like I want to get through as many load cycles as possible, and so I'm running Y Cruncher with 20-second cycles instead of the usual 2 minutes, because 2 minutes, I think we'd get only like one load cycle, and Y Cruncher is noisiest right at the start. Um, so the actual Y Cruncher captures look like this. And this looks like an unintelligible mess because it pretty much is an unintelligible mess. And the reason this happens is because Y Cruncher is a very memory intensive workload. So the CPU is constantly stalling and running based on, is it capable of accessing the memory quickly enough, right? So that creates this sort of random noise pattern that we see here. You can still kind of make out the Windows event timer, at least, yeah, that about lines up right. If this is 10 milliseconds per division, then yeah, this should be about 16.25. So the Windows event timer is just about visible, but it's honestly kind of buried under Y Cruncher's own. It's not really load cycling, it's just the way the workload behaves. And the reason I'm testing it is it gives us a more, like where Prime 95 is a very rigid workload, Y Cruncher is much more dynamic. So, I'm kind of hoping that it'll show different results, which it kind of does, but at the same time, there is difficulty with actually interpreting the Y Cruncher results because, unlike with Prime 95, I don't know if this is, like, depending on what LLC level we're at, I don't know if this is undershoot or if it's just pulling that much current, right? Like, if the current draw right here is, say, I don't know, 200 amps, and the average current draw of the workload, because the target voltage for this is an average voltage of 1.21 volts. Again, I mean, it's not entirely limited by cooling, but because, again, I don't know where the peak current for Y Cruncher is like, I kind of want to be gentle with the voltage settings for it. AMD's boost algorithm will actually run it at around 1.3 volts, but yeah, I'm like also when I'm in the higher V droop LLCs, like the set voltage is getting kind of ridiculous. So yeah, so I could probably run Y Cruncher with slightly higher voltages, but I want the CPU to, like, I want to use the CPU for testing a lot of motherboards, so I need it to not die by some stupid mistake on my part, which I have done. Like I accidentally started Prime 95 on the Y Cruncher settings, which not good. Not good at all. Yeah, it turns out when you shove 1.2 volts into a CPU with a workload that overheats, like is maxing out the thermals at 1.095, yeah, the CPU hits the thermal protection in like a couple seconds. At least I know that works. But that thermal protection kicks in at 115 degrees Celsius, which is very concerning. Anyway, so back to the issue. So, if I'm targeting the average voltage of 1.21 volts, which is around here, is it? Yeah, okay, it might be a bit lower. It might be like there. But anyway, so, my target voltage is 1.21 volts, and if the average current draw of the workload is 140 amps, then like this may or may not be undershoot based on how much peak current there is. And this may or may not be overshoot based on how much immediate current there is, right? The problem here is like, yeah, the average current might be 140 amps, but I don't know the exact current at any given moment in time here. Unlike with Prime 95, where, I can very confidently say that the average current, like the current draw here is a pretty constant 200-ish amps. I don't know how low it gets during the spike. Like, I don't know if it drops to 20 amps or 50. Don't really have any way of, like, figuring that out. But I do know that, like, in the constant load part of this, it's pulling a pretty set amount of current. Whereas with Y Cruncher, that's a problem. I don't know because I don't have a way to get that data. I'd need a motherboard that's, like, modified to measure the Like, I actually have, like, I do have a vague idea of how I could measure this, but it's not, like, fun to do. Um, so, anyway, that's that. So Y-Cruncher is like I think it's still an interesting data to have. It's just less useful because of the whole like I don't actually know how much instantaneous current there is flowing through the CPU at any given moment. Anyway, so that's the test scenarios and the test setup. Let's talk results. Actually, before we get to results, I have one major frustration with both of these ASUS motherboards. When you set the voltage manually, like the core voltage manually, it breaks the SVI3 core voltage reading. I don't know why that happens. It doesn't break, like you setting the SoC voltage doesn't break the SoC voltage reading, but setting the core voltage breaks the core voltage reading. On the Hero, this isn't a complete catastrophe. And when I say it breaks the reading, it gets stuck at like 1 volt, which I know for sure it isn't. So, yeah, I don't know how ASUS managed that, but yeah, they did. To be fair to ASUS, there are other motherboards from other manufacturers in past generations that also had the same issue where it's like, oh, you set the voltage and then you can't get the SVI3 reading working. And the reason I find that very frustrating is the SVI3 reading is dye-sense voltage. So that is a voltage reading from the VRM controller. And what the VRM controller is measuring is dye-sense voltage through some pads provided by AMD on the CPU. So, you know, for getting a really accurate, relatively accurate average voltage measurement, that is sort of the best sensor that you have. So I'm quite annoyed that it doesn't work when you set the voltage manually. On the Hero, it's not a total disaster because there is some extra circuitry on that board to copy the dye-sense voltage over to the Super I/O, but the Super I/O has 9 millivolts of resolution, which is really annoying when the SVI3 reading usually has 1 millivolt of resolution. So, yeah, not thrilled about that. And the Strix ITX board is just, this is blank because the measurements from the Super I/O on that board are unusable because that circuitry that the Hero has to copy the dye-sense voltage isn't present. So when you manually set the voltage on the ITX Strix board, you kind of have no idea what the dye-sense voltage is anymore because the only voltage reading you have accessible to you is the motherboard's power plane, which sits way above what the CPU is actually receiving, just due to the resistance of the CPU socket and the CPU package itself. So, yeah, that is pretty frustrating. Luckily, I do have a voltage measurement that's from the CPU package bottom right corner is far away from the VRM. So that's on boards where I have dye-sense voltage readings working, it's very close to dye-sense voltage readings. So that. And also, if you're wondering what's with the digital multimeter column, that's for me to check that the oscilloscope is wired up correctly. There shouldn't be too much of a difference between the multimeter reading and the oscilloscope reading if everything is hooked up correctly. In the past, I've had issues with the little wires that I have coming off of the CPU breaking. And then what that would produce is the average voltage just goes out of whack. So, yeah, that's what that is for. Anyway, so let's talk about the Hero first. The first thing I'd like to point out is that the absolute best voltage regulation that the Hero can deliver is actually really, really good. First of all, this right here, 23 millivolts average undershoot and 26.6 millivolts average undershoot with so I first got this result, right? That's why we have this retest over here. So I got this result and I was like, there is no way. This is way too good. So I ran it again and I got a result that, as far as I'm concerned, this is functionally the same thing. So the Hero, if you run level 5 load line calibration and then you tweak the switching frequency and the power phase response to 650 kilohertz and ultra fast power phase response, it just delivers incredible voltage regulation. And the settings I'm talking about are these ones right here. So what's cool is actually ASUS does recommend level 5. And what's interesting with level 5 is if we go back to this, even without the tweaks, level 5 already delivers 30 millivolts on average undershoot and 54. on worst case scenario, which is better than level 6, level 7, or, level 8, all of those. It just beats those. What's kind of wacky though is level 4 is like terrible. I don't know why that is, but yeah, level 4 just mega sucks, which is okay. And level 3 behaves like level 5. And the thing is, the expectation is that going from level 5 to level 4, you should basically get the same result as level 3. So I am not sure why level 4 is so bad, but it is. And that happened, like, I retested it, and the funny thing is it's also really bad when running Y-Cruncher, right? Like, you can see we go from 51 and 65 for level 5, or 50 and 77 for level 6, and we go to 56 and 77 on level 4. So, yeah, level 4 on the hero is just like, don't use it. It's bad. I don't know why it's bad, but yeah, it is. And then, yeah, level 5 being recommended, like without tweaking the VR, like without further tweaking the VRM settings, it does deliver basically comparable voltage regulation to level 3. So that's cool. It really is like the best LLC level that you can set. And then if you do tweak the settings, it just gets ridiculous. Like 23 millivolts and 35 millivolts. Like that's just, like as far as I'm concerned, it can't actually get any better than this. So to give you an idea of what a difference that is, let's go back here. So this measurement is from level 8, and this is level 5 tweaked, and this is way zoomed in. All right, so what comparison? Let's see, DS. I should have labeled these better. Oh, so this is level 5 without tweaking, right? And you can still see that, like, yeah, we've got some, well, level 5 without, this is level 5 without any tweaks. And if we zoom in on that, like, you can see, okay, there's some pretty significant undershoot here, right? We go from, like, here to here, and then you can see how the voltage recovers. But if you tweak the LLC settings, like, it basically becomes hard to trigger on, like, it becomes really hard to trigger on the undershoot because there basically isn't any. So, yeah, I'm extremely impressed with the voltage regulation capabilities of the Hero. Though it is not the absolute best board out of the boards that I've measured so far. I also have some other captures, like this is level 4. Yeah, see, level 4 is just like, I don't like this. What is this? Like, that's just horrible. Yeah, and then it was zoomed out level 4, just like, I don't know why it does that. It just does that. And this is, yeah, this is level 4, but without any mouse input. So for some reason, it just, like, level 4 just really doesn't deal well with mouse input, but otherwise it's kind of okay. Though even level 5, like, if you look at level 5 untweaked, you can see, like, the Windows event timer is no longer causing any significant undershoot. It's only mouse input that's really causing any amount of undershoot. But then when you tweak the VRM settings, like, that goes away. So that's really, really cool. I am very impressed. Like, 23 and 35 millivolts like, for both undershoot measurements is just like, that's crazy. And I should, I guess, point out that the average undershoot is, like, across all of the measurements taken, it's averaging the lowest voltage recorded over the measurement period, and the worst undershoot is the absolute lowest voltage recorded, right? And so basically what this is saying is that this 35 millivolts of undershoot versus this 54 millivolts of undershoot says that the undershoot is relative to the average voltage, right? So basically this is saying that the lowest voltage relative to the average was only 35 millivolts below the average, whereas here was 55 millivolts below the average voltage. So yeah, level 5 with tweaks is just, like, really, really good. I also checked if, like, setting the power phase control to extreme would work. It kind of... No, extreme is this one, yeah. So extreme, not worth using. And then lowering the switching frequency, which yes, I do realize that on paper, lowering the switching frequency should always make voltage regulation worse. But I've had some old motherboards back in like the Z390 days where actually lowering the switching frequency would improve their voltage regulation, which was just a quirk of how those VRM controllers worked, which was really funny because the boards would ship from the factory at like 400 kilohertz switching frequency, and then if you turned them down to 300 kilohertz, they would actually get a couple millivolts better voltage regulation. Unfortunately, the Hero uses a voltage controller that doesn't do that. So, um, yeah, best possible settings is 650 kilohertz ultra fast power phase response, and like it just like we're getting voltage regulation where it's like I'm struggling to capture undershoot, which is like I'm very impressed with that. Um, Anyway, in the Y cruncher test, the Y cruncher test is kind of interesting because there's much less difference between the different LLC levels, like level 8 and 7, kind of the same. Then we get to level 6, which is a slight improvement over level 7. Level 5 is a slight improvement over that. And then when we get to level 4, it just gets worse, which I mentioned earlier. So, yeah. So again, level 5 is best. Interestingly enough, for the Y cruncher test, tweaking the VRM settings didn't actually achieve anything. Oh, and I also wanted to see if like, hey, if level 5 can see like this pretty substantial improvement by tweaking the VRM settings, does that same thing work for level 6? And the answer is no. Level 6 with the default VRM settings delivers basically the same performance as with tweaked VRM settings. So, yeah, it's only level 5 where that actually works. I'm not sure exactly why that would be, but I'm guessing it's just like level 6 is just too shallow to be fixable with some extra switching frequency. Um, so anyway, let's move on to the ITX. Now, interesting thing with the ITX is it seems to have like slightly different, like it just has slightly different load line settings compared to the Hero. So for level 8, we have like, I need to set it to 1.115 to get 1.093 volts at the CPU, whereas on the Hero, it was 1.1 volts to get 1.0944. So yeah, the ITX basically seems to have slightly more VDroop just across. It's not actually across all of the LLC levels because level 5 lines up and level 4 lines up, right? 1.3, 1.255. But level 8 and 7 are droopier on the ITX, and level 6 is also slightly droopier on the ITX. So that's kind of interesting. Other than that, the main advantage the ITX has over the Hero is that just across the board it has less overshoot. Not that that's a particularly significant difference. Like I mentioned earlier, overshoot only really matters if it gets so high that it could harm the silicon, which even on the Hero it isn't. Okay, so it's like the whole like, oh yeah, the ITX has better overshoot is like neat, but whatever. Like doesn't actually matter. I just want to point it out because it makes sense for the ITX board to have less overshoot because the ITX board has significantly more bulk capacitance than the Hero does, which is weird because you'd think the bigger board would, have more capacitance. The bigger, more expensive board would have more capacitance, but yeah, no, it doesn't. The Hero's bulk capacitor configuration is actually really wacky, which we will get to. Though at the end of the day, it does deliver very good voltage regulation performance. It's just like, yeah, it's a bit weird. Anyway, again, level 5 is the best, and the tweaks that worked for the Hero also work on the ITX. The ITX already on just untweaked level 5 is slightly better than what the Hero is capable of. I think this is mostly down to the capacitor differences between the two boards. And then when you tweak it, it just like is just amazing. 23 millivolts and 30. That's just like, why can't I have that VRM on the Hero? Okay, to be fair, they're within 5 millivolts of each other, so not really that, like, it's not really a significant difference, but still extremely impressive. Yeah, and then again, I tried if level 6 wouldn't benefit. It really I mean, I guess a little bit, but not really. I wouldn't, yeah, like 3 millivolts, I'd say that's basically margin of error there. And even here, like this, I'd say, yeah, that's margin of error, but that's actually like 15 millivolts. That's outside of margin of error, in my opinion, for this testing. Level 4 on the ITX isn't randomly terrible. So that's a thing, I guess, but I wouldn't bother using level 4 anyway because level 5 is already very, very good. But it's nice that like level 4 doesn't have whatever weird issue it has on the Hero board. And then in Y-Cruncher, we kind of get very similar results to the Hero. I mean, obviously with less overshoot, so lower max voltages, but yeah, we see sort of the same thing where like level 8 and 7, well, actually level 7 on the ITX is significantly better than the level 8, but that might just be because level 7 has like more V-droop than it did on the Hero. Level 6 is basically the same as what we got on the Hero, right? And then level 5, level 5 through 4, even with the tweaks, again, the tweaks just don't do anything for Y-Cruncher, so yeah. And then, well, level 4 isn't randomly terrible, but as far as the actual results go, basically comparable to the results from the Hero. So in the Y-Cruncher test, I'd say the boards are equal. I mean, you know, technically the ITX has less overshoot, but like I said, it really doesn't matter in this scenario. Like neither of these boards has enough overshoot to be concerning. So yeah, so the ITX has a slight edge over the Hero, which is what you'd expect because let's take a look at the actual physical hardware of these two boards. So if we look at the Hero, like I said, the bulk capacitor configuration on this board is kind of whack. Most motherboard manufacturers would just slap like 8 560 microfarad bulk caps through hole bulk caps onto the Vcore VRM and call it a day. But here, like ASUS was like, no, we need 2 560s and 2 100s and 2 150s, which is just the most random mix of capacitances ever. Yeah. So, well, actually, it's not completely random, but the two 100s are basically the same capacitors that they use for like filtering the 12-volt power rail, because those are 16-volt, 100 microfarad capacitors, which are used elsewhere on the board for filtering 12 volts. But yeah, it's still random that these aren't just two 560 microfarad caps, because funnily enough, there are other motherboards in the ASUS lineup that use a very similar voltage regulator and then different like more capacitance than what the Hero has. But yeah, so on the front of the board, the Vcore filtering is these two capacitors, and nope, these two capacitors. And then on the back of the board, we also get these two over here. And so in total, the board has just over like 1600 microfarads of bulk capacitance, which is very, very low for like bulk capacitance on a, you know, power rail that can peak at over 200 amps. Another interesting thing about the Hero is that ASUS decided that apparently all of these multi-layer ceramics in the socket are just completely unnecessary. This one is for memory power, so that one like isn't relevant to the Vcore measurements we're doing here. But yeah, so I find that very interesting. Fortunately, I do have a ASUS X670 board, which has a very similar VRM, but with way more capacitance behind it. Because yeah, instead of using this like mishmash of small through-hole, like small capacitance through-hole capacitors, it uses, I want to say 4 820 microfarad through-hole capacitors. And then I'm not sure if it actually bothers with having these, but it does fully populate the CPU socket because this is actually the same like footprint for capacitors that ASUS used on their X670 boards. They're just not populating it as much as they did on the X670 boards. I'm assuming they basically figured out during the X670, like during the production of the X670 boards, I guess they figured out that this is mostly unnecessary, and that's why they decided to just remove it from the 800 series boards. But yeah, it's still something I want to get comparison measurements for if possible. Now the ITX looks like this. And the Vcore filtering on this board is just all these capacitors over here. And these are 3-terminal SP caps from Panasonic. As far as I'm concerned, this is the best kind of aluminum polymer capacitor you can get, because they, like, the 3-terminal variant specifically exists to reduce the equivalent series inductance. And then also you can get these in like 3 milliohm ESR, whereas through-hole capacitors like the ones we have on the Hero, these basically don't go below 5 milliohm ESR, which is still really, really good, but it's not 3. so yeah, so these are lower ESR, much lower ESL, because even the 2-terminal variant of aluminum polymers already has an equivalent series inductance advantage over through-hole capacitors just due to the physical shape of the capacitor itself. And then the other thing is there's 8 of these, and they're 470 microfarads each. This has over 3,000 microfarads of bulk capacitance. It basically has like more than double the bulk capacitance of the Hero, which is kind of wacky because this is an ITX board. Right, so you'd think like the Hero would have more, like there's more space for capacitors on the ATX board. Why does it have less capacitance? So in a way, like it's really impressive that the Hero delivers as good voltage regulation as it does, considering how little capacitance there's actually on the board. But at the same time, it's like, yeah, but if you have more capacitance, you do actually just get less overshoot. So yeah, and then the other thing is the ITX board has a completely different approach to the capacitors inside the socket itself, though I don't know how it actually like adds up, because I don't know the capacitances of these capacitors, and then especially these. Like I could desolder the multi-layer ceramics to measure them, but I am not desoldering that. Those are tantalums, and I have yet to successfully desolder one of those without burning it, so I'm not even going to try, because I quite like this board. Especially after the measurements I just got off of it, right? Like, really like it now. So yeah, other interesting detail with the Hero is that we do have these little multi-layer ceramics up here, which like that's like an ASUS edition, because obviously the whole like, oh yeah, you should put capacitors over here, that's standard across all motherboard manufacturers. But ASUS, and they've been doing this for a very long time, is they will sometimes just add like multi-layer ceramics on the top side of the PCB, very close to like as close to the CPU socket as possible, which I don't know how beneficial that is, but it definitely doesn't hurt. Though, interestingly enough, compared to the X670 boards, yeah, there's actually less of those too. Right, this is a X670 Pro Art, and you'll notice that it has more of those. So again, I guess ASUS just figured out that that third group of multi-layer ceramics evidently doesn't make enough of a difference to bother keeping it on the board. Oh, and then here you have, oh wait, yeah, no, so that X670 board just has way more capacitance. So that should be interesting once I get the measurements off of that. Anyway, either way, I am still really impressed with the results that the Hero and the ITX got. Yeah. So both really good. The absolute best possible settings are level 5 LLC with the increased switching frequency and the power phase response set to ultra fast. But again, if you're running the CPU stock or running PBO, you can just leave it on level 7 or auto or level 8. There's really no reason to be concerned about undershoot if you're on AMD's boost system. So yeah, that's it for the video. Hopefully you found this somewhat interesting. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support the channel, there are links in the description that you could check out. That would be very much appreciated. And that's it for the video, so thank you for watching, and goodbye. And where did my mouse go? Oh, there it is.